Okay, so continuing on with class 21, here's another example, 6.6. And I'm either going to skip this one or I might skip one of the other two ones. I'm not sure because we do have another section that we need to get to by way of my planning. But if we run out of time in class 21, we'll continue on to class 22, which is the polytropic processes. I went ahead and removed some stuff out of that class 22. So hopefully we won't pile up, and we'll be able to get enough stuff done so that everybody can do homework number 9 all the way through. So anyway, here's example 6.6. We have 1 kilogram of air. It's contained in a cylinder filled with a piston, and there's a pressure of 400 kilopascals and a temperature of 600 degree Kelvin. The air is expanded to 150 kilopascals in a reversible adiabatic process. All right, so this is an important thing. We're going to set this thing equal to 0. Calculate the work done by the air. All right, so we have to put our thinking caps on and figure out what's taking place. So, and we didn't say anything about constant specific heat. So let's go ahead and use a non-constant specific heat process as part of this, right? Because we have 2 temperatures that were taking place. Right, we're coming, excuse me, we have this, so, oh yeah, we have to figure out what the second temperature is going to be. So that's going to, what we're going to do is use what we know about this. So this is like another usefulness of that standard entropy table here. I'm going to write down some things that I know. The mass is equal to 1 kilogram. It's air. T1 is 600 degrees Kelvin. P1 is 400 kilopascals. P2 is equal to 150 kilopascals. Okay, it's a reversible adiabatic process. Therefore, delta S is equal to 0. Q 1 to 2 is equal to 0, right? Adiabatic means this, reversible means this. And is that true? Reversible and adiabatic do mean this right here, but I'm going to say that we have reversible processes that do change in entropy. So we have to be careful because we know that an isothermal process does change in entropy. So I can't say that this 100% means that entropy is 0, but there you go. So one equation that we can use, so here's going to be the main guy here. We're going to say that we have ST20 minus ST10 minus R ln of P2 over P1. Okay. So let's go ahead and look up in table A.7.1, because this is air, and find out what this is and also what U is going to be. Like, how do I know that I'm going to need U? Well, let me go back up to the conservation of energy, aka the first law. It's always a good guy to go back to and trying to work out, puzzle your way through the thing. You're going to have U2 minus U1 is equal to Q1 to 2 minus W1 to 2. But we know that this is adiabatic. So we're concentrating on U's, right? So that's being detectives. We look through here, we say, well, this is 0, and we're looking for work. What are we going to do? Let's find, we have a container of air. We might maybe draw the thing for ourselves, and all of a sudden, hopefully, that image right there of a chunk of mass reminds us that we're going to use the first law for a particular chunk of something, and we're going to use internal energy. So let's look up. That's kind of like an in-between thought right there. Let's look up here at T1 is equal to 600 degrees Kelvin. We don't know what T2 is, but we might be able to figure it out by way of this equation right here. And then when we have to do the work, we'll use this equation. So look right here. Is this for air? Okay, we already have it. All right, so from the thing for the previous guy, we had that this was 7.57638. And we also need to know this though now, right there, right? So we're going to write those guys down. We're going to have ST10 equal to 7.57638 kilojoules per kilogram degree Kelvin, and we're going to have a U1 is equal to 435.1 kilojoules per kilogram. All right, so coming back, we have those. Well, now let's go plug this in and say, well, that's going to be 0 is going to be equal to ST2 minus, here's my ST1, we just got that, 7.57638, and then minus, we didn't write, oh, we had it from the other previous one, 0.287, right, we got that in the last example, get rid of this, and the natural log is going to be P2 was 150, and this is 600. All right, so plugging through here, we can find ST2, 0, is going to be equal to 7.2949. Now let's work backwards. Let's say, okay, well, this is going to be you know, and this is just saying, well, we know this is isentropic, it's equal to 0, so the only way to make this 0 is to find out what this thing is, so that's going to be this value at the end. So let's go ahead and look him up, and then we can find what the temperature is going to be. So let's see, 7.29, it's going to fit right between this guy and this guy, which is here and here. So we could do both interpolations, and we know the temperature is going to be somewhere between 440 and 460, and it's probably going to be closer to 460 than it is 440, because this 7.29 is closer to 7.3 than it is to 7.25. So interpolating away onto this thing, let me put them up into here. So here's our 7.2949, and I have the above one at 440. Let me write this one down, 440 and 460. This is 7.25607, barely fit in there, 7. And then this is 7.30142, and so this is T2. Interpolate, interp, and we get T2 is equal to 457.1 degrees Kelvin. All right, but the thing that we're probably going to be more useful to us is find out what U is going to be. So we can either do it based on temperature, or we could do it based on U's, but I'll go ahead and, I mean based on entropies, we'll just do this again. 25607, 7.2949, and 7.30142, and the U above it is 315.64, the U below it is 330.31, and this one's going to be U2 is what we're going to try to find, and we get U2 328.20 kilojoules per kilogram degree Kelvin. And so if we plug back in up to here, and we get 328.2, and by the way, what we should do is multiply it by these little u's. So let's multiply it by 1. That's the kilograms. See, it's per kilogram. And but I accidentally put degree Kelvin in there. This does not degree Kelvin. Remember, that's just internal energy. It's usually kilojoules per kilogram. So I forgot. And we have 435.10, And remember that we had a negative up here, work from 1 to 2. Remember, right there. So 2 minus 1, even though this one, 2 is less than 1, so that's going to get rid of that. Yeah, and then so we're going to have work 1 to 2 is going to be 128.9 kilojoules per kilogram, right? Taking place right here, and this is going to be work out. That's why it's positive, right? So we're allowing the thing to expand. It was went from a high pressure to a low pressure, and went from a the temperature, but even though the temperature dropped from 600 Kelvin to 457 Kelvin, the pressure decreased. So we actually had work coming out, work out. And we could probably go ahead and insulate that thing to make it adiabatic. Remember though that this was done in just such a perfect way to make it reversible, right? There's not many real reversible cycles, so they just went ahead and said, well, we're going to do it like maybe really, really slowly in little tiny increments, and somehow make sure that we can return right back to the thing. So that's 11 minutes. We have another topic for this. I think it's going to be too much, but it's a satisfying topic. I like it because it scratches an itch I think you would have, where we're going to explain at least some of these mysterious equations. In the next class, we'll get to even some more, but some of these guys are here. It's really all about the isentropic ones. So we'll talk about this system right here, and we'll get to these equations, which we haven't had before. So that's what's coming up. Talk to you then.